Good morning. This is a short video here. We are going to describe the problem of decision trees, as I call it here. So this is going to be very short. Um, a couple of assumptions to make here. I seem to be having some difficulties. Why won't my... We'll do that. Okay, very good. So a couple of assumptions here now. We're going to have a table of data. Again, we're doing supervised learning here, so let us recall what that means. We are trying to be predictive about a particular experiment. The experiment here is we're trying to be predictive about whether students are going to receive an A or not. And we're making the assumption that whether they get an A or not is based upon their height and their weight. But as we say right over here, the data is categorical or nominal. That means that the height and the weight are not going to be described by actual numbers, but instead we're going to have groups of categories. For height, we're going to classify the students as either being tall or short. And for weight, we are going to classify the students as being either heavy, medium, or light. Now, what those actual adjectives translate into is something that we'll need to figure out later on, but let's for the moment assume that we've already done it. Later on, we'll be able to apply some of these ideas to attributes that are numerical, but for now, we're going to just restrict ourselves to nominal data. So we're seeking what's called the best solution, and that of course raises the issue, what is the best? So we come over here to the next slide, and for a moment I just ask you to turn your attention over here to the right side of the page where we have our data. There's not a whole lot of data here, just 4 instances, and we've actually labeled them 1 through 4. And we can see here that we have the height, tall or short. The weight could either be light, medium, or heavy. And then whether they're an A student. We're not saying they're a student, it's a student. So for example, we can see that if you're tall and heavy, you're an A student. And what we're trying to do is we're trying to be predictive here. In other words, let's imagine in comes some other student now that we haven't seen before, but we can record their height and their weight, and then we're trying to predict whether they're an A student or not. Now, what we're going to do over here is we're going to create what's called a decision tree. So now we can turn our attention over here to the left. So at the top of the decision tree is actually all of the data. In other words, all 4 of these instances, okay, are sitting right up here at the top. And what we do is we're going to arbitrarily pick an attribute to see if we can split this tree up. So the attribute that I pick is height. And when I pick the attribute height, I can either have values of tall or short. And when I look at tall, that's going to bring 2 of these 4 instances down over to here. So amongst the tall, I get instance number 1 and 3. And I note that for instance 1, that's a heavy person, and that is an A student. And I note over here that for instance 3, I get a medium person, and no, they're not an A student. If I come over here and I go to instance short, number 2, I get a person whose weight is light, and they're not an A student. I have instance 4 where the student is heavy, and they are an A student. Now the point is that when I've picked this attribute height, I'm down to these 2 nodes in the decision tree, and these are not what we call pure nodes. Pure nodes would be nodes that are either all yeses or they would be all nos. So I still have another attribute available to me, and the attribute now is weight. So I come over here under tall and I say, well, weight, I can either be heavy, medium, or light. And I notice what happens is attribute number 1, okay, or instance number 1, comes down here to heavy, and yes, that is an A student. And instance number 3, okay, that comes down here to medium, and that's a no. So all of these instances have now made it down to here, and I've got pure nodes. Likewise, if I come over here to short, I can see that instance number 2 is light, and that's a no. So I come over here to light, and I note that there's a no over here. And I know that instance number 4 is heavy, and that's a yes. So now at this level, I'm happy. And the reason why I'm happy is because I have all pure nodes down here. And if I wanted to come up with a rule for what makes an A student, I just start up at the top and I follow these down to all of my yes instances. So I come over here and I go, what is the rule for an A student? So the first part of it is if height is tall and weight is heavy. So if I come over here, if height is tall and weight is heavy, that's one instance. Or if I start up here and height is short and weight is heavy, then I have an A student. So the rule for an A student is to follow it from the top of the tree all the way down to a leaf node that is a pure yes. Okay? And we have 2 ways in which to do that here. And of course, to make that into one big rule, we say it's either this path or it is this path. That's why we have this logical connector over here, or. Now, I hope that you all look at this and say, well, okay, that seems to work, but why didn't you pick attribute weight first? Because if we pick weight, we can see right over here that both of our instances for heavy yielded yes, and that would give us a much shorter decision tree. In other words, if I had made a decision tree where I said attribute is weight, and I came over here to heavy, I'd have 2 yeses over here, and I would come over here to medium and light, and those would also be, I apologize for this thing moving around, those would be no's, okay? I'd have light as no, medium no, but I'm interested in just the yeses. And the beauty of that is that would be a better solution. We make a definition that a better solution is one that gives us a decision tree of lesser depth, so that picking weight first would give us a tree that really has, we would start off at the top and then just go down one attribute. The depth of that would be 2. The original tree that we had over here, the depth is 3. There's 1, there's 2, there's 3. Remember, what you're not seeing here at the top is the node that has all 4 instances in it. Then we pick an attribute, we have this, then we pick another attribute. So it's a height of 3, but over here, it would be a height of 2. We can see we can't get any shorter than this, okay, unless the thing was just all yeses to begin with. That is certainly a possibility, in which case we probably don't even need to consider a decision tree. So the question comes to, how do I find the tree of minimal depth? And it turns out that that's an intractable problem. Intractable doesn't mean it's impossible, it just means it would take a very long time. Now, in this particular example, where there are only 2 attributes, that's not bad. But I want you to imagine that instead, suppose we had 10 attributes. Well, then we would have to consider all the possibilities. Now, if there are 10 attributes, there are 10 different attributes I could consider one down in the decision tree. And then underneath each one of those, there would be 9 possibilities. And then underneath each one of those would be 8 possibilities. So there are over n factorial possibilities, and if you do some quick mathematics, n factorial is bigger than 2 to the n, so this is actually an exponential problem. There is no known solution for solving this problem that isn't exponential. But what we're going to be considering here is a heuristic, even though it's referred to as an algorithm, it really isn't. And what a heuristic is it means that we think that this recipe provides us with good solutions, but we can't guarantee us that it gives us the best solution. And the name of the algorithm is called ID3, and it was developed by an Australian statistician. His name was J. Ross Quinlan. And it's based upon picking the attribute that reduces the overall entropy in the tree. Now, we've already discussed entropy. Maybe it's not clear to you at this point what the overall entropy in a tree might be, but that is what we will be discussing next. Thank you.